Okay, thank you. So hello everyone, thank you for attending this presentation. So I'm going to talk about the interaction between the internal and local currents in the Cassidaigne submarine canyons and sediment transport and sedimentary deposits brought by gravity-driven turbidity currents. So on continental slopes, gravity currents are mainly observable at the level of submarine canyons, which constitute a zone of exchanges of water masses between the continental shelf and the deep sea. They provide an ideal pathway for sediment transport driven by turbidity currents and associated to relevant amounts of nutrients, oxygen, carbon, but also pollutants such as microplastics, for example. From the shelf to the deep sea, turbidity currents may be first modulated by alongshore regional currents before entering the submarine canyon. The latter may locally trap momentum and energy so that gravity currents can interact with some processes such as tides or geostrophic flows. And finally, they may interact with bottom currents, closing the thermal circulation. So those currents, those interactions between local currents and turbidity currents were also illustrated with some experiments, such as this experiment led at Utrecht University in 2019 to demonstrate the interaction between contour current and turbidity current. It was found that contour currents are able to modulate the sediment transport by partially blocking their deposition and modifying the direction of their dispersion. And those experiments allowed us to conjecture that the interaction between contour current and turbidity current are observable at the level of sediment-rich submarine canyon where a relevant amount of water masses are transported. That's why in this study, we are interested in such currents at the level of the Cassidaigne Canyon, located at the entrance of the Gulf of Lion in the Mediterranean Sea. Indeed, during the Messinian salinity crisis, the sea level of the Mediterranean Sea was at least 100 meters lower than today, exposing the head of this canyon to the open air. Consequently, it was carved out by winds and rivers before being eroded by the currents. And that's why the Cassidaigne Canyon is a steep and narrow subaerial canyon, different from the other canyon in the Gulf of Lion. So let's now look at its morphology in a little more details. So for 48 years, 20 to 32 megatons of red mud have been discharged into the Cassidaigne Canyon, creating a sinuous channel of more than 10 meters deep. And this input of sediments in the Cassidaigne Canyon has created an artificial turbiditic system with the same erosion and deposition patterns as a natural system, as we can see here. So these results were obtained thanks to samples in 2019 based on coring, AUV multi-mountain beam, eco-sounding, and sediment traps. Here, at the gorge of the canyon, or at the gorge which links the canyon to the open slope and the sedimentary ridge, we can observe that the canyon is fed laterally by gullies and channels that overlay the main talweg. And by considering the direction of and intensity of this undercurrent on the slope in the vicinity of this drainage area, it can be assumed that fine sediment available near the shelf rim are transported into the canyon. So to identify the physical processes in the Cassidaigne Canyon, the CASSISAID oceanographic campaign was led from March to November 2019. It was based on the installation of 4 ADCPs, so a benthic ADCP at the head of the canyon, 2 Pierre-Gint ADCP located in the canyon and equipped with turbidimeters, and a deeper Anitra ADCP. Apart from the benthic ADCP, the other moorings are equipped with sediment traps, and those devices allowed us to gather data on currents, temperature, but also sediment transport in the canyon. And we were then able to identify many processes in the Cassidaigne Canyon. Indeed, the Cassidaigne Canyon is located in an active circulation area where water masses are subject to two forcings. So first, the northern current, which flows offshore and may intrude the Gulf of Lion. And second, a north-northwest wind, which influence the superficial water layers, thus favoring upwellings, the strongest of which is located at the level of the Cassidaigne Canyon. Moreover, the water column is characterized by a strong stratification in the spring-summer. And this stratification can be influenced by the northern current. Indeed, the northern current manifests itself in the form of meanders that may intrude the Gulf of Lion, and this entry can be favored by easterly winds. And in those cases, the transport of water in the canyon is influenced because shear currents are homogeneized over the entire column, as we can see on this example recorded on October 24th during a storm event. And during those phenomena, the currents reach the shelf bed with enough energy to move the local sediment, and those phenomena depend on stratification. So here, during the Cassidaigne oceanographic campaign, we can distinguish two periods. First, a stratified water column from May to October, and second, a homogeneous water column at the beginning of the campaign, especially in March. During those two periods, the sediment traps placed on the different ADCPs allowed us to highlight the sedimentation fluxes in the canyon. So first, during the stratified period, the upper Peregrine ADCP, in blue here, allowed us to record the normal cycle of marine flow characterized by high sedimentation fluxes due to the canyon confinement. And the variation of those fluxes depends on some biological activity. In contrast, during the homogeneous period, the two deeper ADCP recorded extremely high values of sedimentation fluxes in 1 week in March, and those values are equivalent to what can be recorded by the upward station over a 4-year period. Then those sedimentation fluxes were linked to turbidity currents thanks to the turbidity meters placed on the two Peregrine ADCPs. So here we can observe from the upward ADCP during the stratified period a slight increase of turbidity currents, which are not recorded by the deeper Peregrine ADCP, except for a few peaks, which are due to a reversal of the flow orientation during strong wind forcing events. To identify the orientation of the flow, a Eulerian hodogram was drawn at the gorge of the canyon during spring-summer and winter-spring. Indeed, a hodogram is a representation of the virtual Eulerian trajectory over time of water mass displacement. And here we can observe, apart from a few periods, a fairly constant upwelling towards the northwest. And on this figure, we can also observe that upwellings are 50% lower during spring-summer than during winter-spring. And during this last period, we can find again in March a strong turbidity current. So let's now focus on this month. From March 11th to March 12th, the benthic ADCP recorded a strong upwelling. And as we are in March, this upwelling wasn't limited by the stratification, so it was intense and deep. And during the same period, the Pergin 2 ADCP here at the gorge of the canyon recorded a strong turbidity event, which was also observed 6 hours later by the deeper Anitra ADCP. So those results allowed us to conclude that turbidity current did originate from the confined area of the canyon and flowed towards the gorge. And so those results allow us also to conclude that upwellings remain capable of resuspending sediment, even if there has been no sediment supply since 2015 into this canyon. So to conclude, the Cassidaigne Canyon is a specific subaerial canyon with a narrow and steep morphology. The deposition of red mud in the Cassidaigne Canyon until 2015 allowed to create an artificial meandering turbiditic system with the same characteristics as a natural system, which allowed us to highlight sedimentation, transport, and turbidity currents in the submarine canyon. Moreover, the Cassidaigne Canyon is located in a dynamic region where it is influenced by local currents such as the northern current, upwellings or downwellings modulated by wind forcing. Those phenomena, coupled with the seasonal cycle of stratification, influence and is able to modulate turbidity currents, which depends on hydrological processes. And finally, a strong event in March allowed us to highlight the link between upwellings and turbidity currents. So to finish my presentation, I want to add that gravity currents and sediment transport in the ocean must be understood and modeled thanks to by considering currents in the ocean, which play a real role in sediment transport and deposition. Thank you for your attention, and I will be happy to answer if you have any questions.
Well, thank you very much for that fantastic presentation, Lenaig. So, are there questions from the audience in the question box? I guess my question would be whether we are sure that the first sediment in the turbidity current was really entrained by the upwelling in the canyon, or could there also be a resuspension event on the shelf which then fed into a turbidity current in the canyon? Can we differentiate between those two sources?
Well, it was concluded that this turbidity current is linked with the upwelling because I didn't show the results recorded by the Bentic ADCP, but there was a real correlation between the event of the upwelling and just after the turbidity current, which was generated. So that's why we concluded.
Convincing correlation. Yeah. Okay.
Yes.